Hi. So this is a tech talk that I had prepared in conjunction with a couple tech events that I was working on for the what we called Augusta Cyber Week that was leading up to Besides Augusta 2024. It got, I guess, hurricaned out, I believe is the term that I had been using. We had Hurricane Helene hit very, very hard in our area. Everything for the whole week was canceled. The big conference was canceled. Myself and some other people involved really were looking forward to what I had been curating, working on, going to be participating in. So we're going to combine those into a future event, and I hope that works out. But I've had a lot of questions on the talk that I was working on. I actually did not finish it, so we're about to see how well I did. This is a first run through of it, and I just really wanted to get it up, so raw and hopefully interesting. But oh yeah, so I don't have my glasses on, so I actually kind of look like my card. You guys get to decide if that looks like me or not. I think I've gotten a few odd looks because I usually have big glasses on, so now I kind of look like that. I don't have a bow tie on though, and I have no makeup. Well, I have the remains of some makeup from being in a wedding party this weekend. I will say I don't advise anyone that is not extremely familiar with long fake eyelashes to go ahead and jump that gun if you are not prepared for it. Just my tip for you before getting on to nerdier stuff. Okay, so see if I can get all the screens going in all the right ways for you. Hi, I'm Sarah with Hack Augusta. I am a self-taught programmer and a full-stack software engineer. I've also filled some CTO shoes and stood in for various oddball tech roles, especially associated with startups in our vicinity or tech events and polyglot conferences, and hopefully a whole lot more to come. One in the works now, actually. I am a member of our host space, the Clubhouse, which is a co-working space, but above all, a community within the greater community of Hack Augusta. Oh, yeah. Hack Augusta. We believe the world is a better place when every community supports its creative class of hackers, artists, makers, and entrepreneurs. We are the creative class that makes cities worth living in. This is STEM. How many of you consider yourself a part of STEM? How many of you consider yourself a hacker, artist, maker, or entrepreneur? How about one but not the other? Anything of the sort? Any reason? Does anyone think they are neither or none of the above? Well, in my opinion, if you are here today, you're a part of STEM, and you are a part of the creative class that makes cities worth living in. The name Hack Augusta comes from the concept of hacking the community to create a culture of innovation and collaboration. This is STEM to me. That's what STEM means to me. And I did not read the part where I want to create it. So when I wanted to quote the beginning of this book, it's really meaningful to me, and I think that it's powerful when it comes from, I don't know if it's coming from an engineer or someone that just believes in the words, but I think it's particularly powerful, so I wanted to quote it, and here it is. I have it here. I'm like, I don't know where the camera's. Yeah. Starry Messenger by Neil deGrasse Tyson. This is the intro to it. Let's see, it is called the preface, just to be super accurate. Starry Messenger is a wake-up call to civilization. People no longer know who or what to trust. We sow hatred of others fueled by what we think is true or what we want to be true without regard to what is true. Cultural and political factions battle for the souls of communities and of nations. We've lost all sight of what distinguishes fact from opinions. We're quick with acts of aggression and slow with acts of kindness. When Galileo Galilei published Sidereus Nuncius in 1610, he brought to earth cosmic truths that had been waiting since antiquity to descend upon human thought. Galileo's freshly perfected telescope revealed a universe unlike anything people presumed to be true, unlike anything people wanted to be true, unlike anything people dare say was true. Sidereus Nuncius contained his observations of the sun, moon, and stars, as well as the planets and the Milky Way. Two fast takeaways from his book. 1. Human eyes alone are insufficient to reveal fundamental truths about the operations of nature. That's actually kind of where math comes in a little bit there. We'll tie into that. 2. Earth is not the center of all motion. It orbits the sun as just one among the other known planets. Sidereus translates from Latin to starry messenger. These first ever cosmic perspectives in our world were ego checks on our own self-importance. Messages from the stars forcing people to rethink our relationships to one another, to Earth, and to the cosmos. We otherwise risk believing the world revolves around us and our opinions. As an antidote, Starry Messenger offers ways to allocate our emotional and intellectual energies that reconcile with the biology, chemistry, physics of the known universe. Starry Messenger recasts some of the most discussed and debated topics of our times. War, politics, religion, truth, beauty, gender, race, each an artificial battlefield on the landscape of life, and returns them to the reader in ways that foster accountability and wisdom in the service of civilization. I also intermittently explore how we might appear to space aliens who arrive on Earth with no preconceived notions of who or what we are, or how we should be. They serve as impartial observers of our mysterious ways as they highlight inconsistencies, hypocrisies, and occasional idiocies of our lives. Think of Starry Messenger as a trove of insights, informed by the universe, and brought to you by the methods and tools of science. This is one of the many things that STEM means to me. And a lot of the event here, the talks are about STEM. I think that Hack Augusta does an very interesting community take on incorporating that into our here and now, in the present, every day, or every week, or every month lives. And I think that's really important. So I wanted to tie that into everyone present for the talk, and I clearly did not involve some notes in that, but that's the beginning. And then the little bit odd tidbits that don't matter so much here, but to join us in hacking the community that we want and deserve, use these QR codes to find me on LinkedIn, join our meetup.com group if you haven't already, or join our Discord. So math. Yeah, let me pause this real quick because here you go. I'm assuming it's recording again. It's funny. It has a pause button and then not like an unpause. But we didn't record all that. Anyway, now I'm using a framework for this. I hadn't used it before. It's called Reveal.js. I have not done slides like this before. I've only done like PowerPoint circa like 2007 mostly. So this has something on where I do the full screen. Some of the pages don't like to be centered the first time you go through them. So I just want to pass all the way down and then all the way back. And here I am. So math. Yeah. I've always loved math, but I never progressed as far as I would have liked and still would like to. I've heard others, programs in particular, say similar things. People seem to think they don't know math. If you just thought to yourself, yep, that's me, today I'm going to try to convince you that you know more than you realize. If you like math or think you know math, let's see if I open your eyes today to anything. And please contact me afterward and tell me about it. I would love to talk math. I do it on a regular basis to people that don't want to talk math. So if you want to, you find me. Number sense. What is number sense? I think I have a strong number sense. It's about understanding concepts like quantities, more and less, bigger and smaller. To understand these concepts is to understand math logic. Understanding math logic is comparable to understanding programming logic. How many of you know what this is? Yeah. Scroll down. How many of you understand it? It's sigma notation. It's summation. It means this. You complete the operation to the right. I can use my mouth here to mouse. You keep the operation to the right, starting at the number defined at the bottom and going to the number defined at the top. You do this for each increment, adding to an overall sum each time. So if I is 1 right now, you're going to have 1 squared. You kind of add that to a rolling total or whatever term seems to work for your brain. I know that bag will be one, or you can stash it, I guess. It's not really the same as summation, but I am rambling with odd terms, so I'm going to move on. So then after you've added that to the sum. Now I will be 2. So you have 2 squared, 2 squared. Then it'll be 3, 3 squared. You're adding it each time to the same sum, getting to the end, depending on what's up here. Oh. How many know what this is? It's a for loop. Guess what? They're the same. I'm going to leave this up for a minute. But I have several ways of explaining it. So, okay. So as I said earlier, let me quote it the same so that it makes the most sense to you. You complete the operation to the right. So we have I squared. I squared. Let's start from the beginning. We're setting I equals 1 both times. So we have I equals 1 down here. I equals 1 right here for our for loop. We have an ending term of 4, ending term of 4 right here, ending term of 4. And then this is the operation that happens. I squared, I squared. So, how many know what this is now? Does it make sense? How about this one? It's a little more complex. Does that make just as much sense? So we're going to start at 1. We're going to have 3 times 1 plus 1 squared. And that's going to be added to a sum. Then we're going to have 2. So 3 times 2 plus 2 squared. And we're going to do that until the number that we are dealing with reaches 42. We're going to include the 42. And it's all going to go into one big sum. All right, so how about this one? Yeah. This is just an interesting one. For those of you following along in the, I think it's called multipass, you'll be able to click on this if you want to. Otherwise, I can provide a link with later, but it is on my LinkedIn if you're finding me. I just found it very interesting. It wasn't that long ago that the article came out and I was reading about it. I liked that they displayed things the way that they did, and it includes it here. So here we'd be having, starting at 1. So n is 1 for all of these things. And then, putting that into a sum. We're going to do that until infinity, though. That's where it gets interesting, right? We won't go into that right now, though. So let's see. Yeah. Number sense. So how many of you at the beginning of this presentation thought you didn't understand it? So have I successfully proven to anyone that you understand more than you think? Maybe. We'll see. Number sense. Math is logic. Programming is logic. Math teaches logical reasoning and problem-solving skills that are essential in programming. It helps in breaking down complex problems into smaller, manageable parts, similar to how you might approach writing a program or debugging code. To quote a friend, my high school geometry class is what helped me to start excel at programming. My teacher taught heavily proof-based geometry, and it really helped me figure out how to break big problems down into smaller ones. All right, so moving on from there. Oh, guess I had a quote there. But random numbers. Why is it difficult to generate random numbers? I think here is where I'm going to touch on the cryptography side of things, depending on my audience. We're probably going to have a mix of both, programmers probably outside of it, and then cybersecurity. So we'll see where it gets interesting, yeah? Generating random numbers is difficult because true randomness is rare in computers, which are deterministic systems. Algorithms typically generate pseudo-random numbers based on an initial value, which is called a seed. While these can appear random, they can be predictable if the seed is known. Achieving true randomness requires unpredictable inputs like physical phenomena, which provide higher entropy, making them hard to predict and ideal for secure applications like cryptography. An example of physical phenomena as unpredictable inputs is lava lamp movements. I know some of you must know what I'm getting at, yeah? Cloudflare uses a wall of lava lamps to generate random data for encryptions. Photos of unpredictable movement of the lava provide entropy, which helps create secure cryptographic seeds for encryption keys. Cryptographic seeds for encryption keys. Yeah, that's funny. I didn't notice that before. This process ensures strong randomness, which is essential for preventing predictable encryption, making online communication more secure. For those of you interested in checking this out further, you are on the multiplex. I said pass, didn't it? I said multipass, like, oh, yep, Yes, I did. Multipass. Okay. You can click the link here because this will be a link. But I assure you, if you search the internets for Cloudflare lava lamp, it will come up. It will. It's very well known. So, pi, because it's not really a math talk, right? Pi, without pi, am I right? Right? I mean, it's got to be somebody here that's like somewhere on the level of a pi nerd like I am. Somebody. Maybe we'll see. Does anyone know why I might be relating pi to random numbers? I kind of hope somebody does. So for the last pi day, I whipped up some code to demonstrate the near randomness of the digits of pi. And I remember how challenging it can be to generate even pseudo-random numbers, which is really not the same level as the secure applications cryptography, but we're just talking about things that we do in, I'll call it everyday code. But let's see. So I used a library to grab pi to 1 million digits, starting to the right of decimal. So say it with me now. I know somebody knows this. Will let their time shine. They've been practicing this in their head for at least 20 years, right? Okay. Yeah. 1415926. Anyway. I use iterations of 10,000, 100,000, 1 million, 10 million, and 100 million. I log all the results so I can compare and contrast between pi and JavaScript's math.random. In this example, I use math.random to get a random digit of pi, but I will show another example as well. So for this one, I am using the math.random because I want to get a random digit in that, I call it pi string. But I do have another way of doing it that I will show after. It's a little bit more simplistic. This is comparing to using math.random without pi. It's just doing the same iterations. So, yeah. Oh, yeah. I'm laughing at my own joke without reading it. I say, here is the numbers printout. Get it? Because everything's about numbers. I'm funny. Okay, so this is all the different iterations. Here's pi versus math.random for the 1,000 loop, 10,000 loop, 100,000 loop, 1 million loop. You can see how these are almost always the same number. It's really impressive. Like, I probably could have tried really hard and tried to find iterations of it that printed out the same exact number for at least one of them once, but I didn't do that. I just ran it once. Tell me in 1 million. Yeah. So then now I am showing the percentage of each just to give a different representation of numbers, because everything's about numbers, remember, but it's just astounding to me how, like, even comparing here, like there's 12 here, and this is what people are using math.random for JavaScript. There's not a 12 here. I know this one rounds up to it, but that's not like the topic for today, so we're gonna pretend. No. It still astounds me. I've showcased something like this about pi in so many different ways to so many people. It still amazes me. Just knowing what I know about math, random numbers, entropy, patterns, sequences, it just still astounds me. It's almost 10%. It's amazing. So 10,000, 100,000, 1 million, 10 million, 100 million. Okay, so this is the other example. Let's see. So I use that 1 million pi string, 1 million digit pi string to count individual digits. So I just go one at a time in the whole 1 million long string. And then, so I'm not using math.random at all. But this is what I'm getting. So this is the count for each single digit because I have the 10 single digits. So if everything was perfectly random, I would have 10% of each, right? It's pretty close, but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The number of times that I'm getting that in the 1 million and then percentile. So number sense. I think it's pretty amazing. But to give another example, oh no, that was the previous one. This is the Euler one. So when I think of number sense, I think of my own number sense. And I think of an algorithm that I wrote to solve an Euler problem. This is for Project Euler. I think I have a link to it somewhere in here. If not, I should probably make a note of that and I will provide you with it. If anything in here, if you're watching this online or in person, if there's any information that you're curious about, feel free to reach out. But yeah, so in order to compute the next triangular number, I feel like there's some missing bits in here. So I'm just going to read it. The sequence of triangle numbers is generated by adding the natural numbers. So the seventh triangle number would be 28 because you have 1 plus 2 plus 3 plus 4 is 5. These are the natural numbers. So if we have 28 as a triangle number, then we're going to add this next one here. So plus 8. And then here's your first terms as examples. So we have the 1, 3. These are the triangle numbers, not the natural number progression. So see how 28 goes to 36 because we are adding that next natural number. And we're going to do that over and over again to generate triangle numbers. So let's see. So in order to compute, let's go back. In order to compute the next triangle number, you are adding the next natural number to the current triangle number. So added together, these natural numbers equal 28. And then 28 plus 8 is 36 right here. And then 36 plus 9, which would be the next after 8, was 45. So on. Let us list the factors of the first 7 triangle numbers. So these are the triangle numbers themselves, which is the same sequence we were just seeing. 1, 3, 6, 10, 15, 21. 1, 3, 6, 10, 15, 21, 28. These are the factors of them. We can see that 28 is the first triangle number to have over 5 divisors. I can't select the same because it's like not, duh. Sorry. What is the value of the first triangle number to have over 500 divisors? So that seems really fitted on that. Let's see if it fixes it. No, it does not. All right, well. Let's see. I did solve it fast, but my algorithm took 10 to 15 minutes to execute on what was a modern laptop with, decent processing power. So I paused. I considered what would make it faster. I assumed the key would be to reduce the search area. It's kind of a given in a few concepts, thinking about mathematic principles, but also just doing coding challenges. And if you've ever done them all, especially as part of your learning, that's something that's been taught, especially has to do with algorithm and searching. So number sense tells me that not only searching through a large amount of individual triangle numbers takes a long time, but also that finding each factor for each triangle number takes a long time, particularly taking into account that the larger the triangle number, the longer it will take to check for factors and count them. So I would love to show what's over here, so I will say it verbally. Taking as an example triangle number 78. What I'm doing is I'm starting from the beginning. I want to find that first factor. When I find that factor, I know what its pair is. So as an example, 1 and 78. If I take that here, I'm always going to assume that divisors are 2 for that reason. Same as factors. Sorry, I could have used that term uniformly. But if I'm finding a first divisor or factor, it means that I'm finding the second one. So 1 and 78 are always going to exist. If I go up and it's an even number and 2 is, then its pair means that there's no numbers that I need to check above that. So as an example, for 78, I have factors of 1 and 78, but that's already given. We're going to loop through. We're going to start on 2. We're going to find that 2 is a factor. So this will be a yes. 2 is a factor. Now I guess this is a resetting to 2. My apologies. So I'm going to find that for 78, 2 is a factor. So I'm going to add the divisors. I'm going to add 2 to the count because the divisors is the count. And I know that the factor pair for 2 is 39. So I now know that I don't need to search for anything above 39 ever. So I'm resetting max. So max is now the triangle number divided by the number we just got. So in this example, 78 divided by 2, so you're going to have 39. 39 is now the max, and we're only going to be looping through max. So I just cut down the search area from 70 to the last place that you're looping through, from 78 to 39. That's dramatic. Think about how massively impactful that would be for really, really big numbers. But I'm going to do that every time. So right now we started at 2. Max was itself, so 78, but we found that it was a factor. So now we're saying, okay, divisors is plus 2 from what we had because we definitely found 1. That means we found 2, and we'll reset max. So max is now 39. So now I is going to be 3, and that is another factor for 78. The factor pair for 3 is 26. So we now reduce that again. And then the next one after that, it'll be 6. So it will loop through a few times, but then it'll find 6. The factor pair for that is 13. And that's it for that particular number. And that's why it's so fast. I don't think let's see if I have anything else. Yeah. So it's how it's fast. It still has to compute all the divisors, but it shrinks the search area so dramatically. And then I am providing the link to the problem. It's the Project Euler problem 12 triangle numbers. And then I have a very poor front end example of what's called Einstein rock paradox. I thought this would be easier. The framework was giving me some challenges. But I think ultimately you're probably better off watching YouTube of it anyway. I did think about embedding that, but this was fun and you can laugh at me all you want. So I love stars. I made my rock stars. You can see that the way this is set up, there's 2 stars in each of the corners. So now if we count our rows and our columns only on the outside, we have 1, 2, 3, 4. Oh wait, this is like part of the slide, so I can just 6, right? 1, 2, 3, 4, 5, 6, 6, 6, 6, 6. Okay. So what happens if we add 1? So what we're going to do is we're going to add 1 here. See how this is now 2? Okay. And then over here, we moved this guy down 1. Okay. So now what do we have? Yeah. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So on and so forth. We still have 6, 6, 6, 6. 6, 6, 6. Yeah, that's 4. So, number sense, right? How many of you are thinking, oh, magical? Or how many think you're like, yeah, because that doesn't affect the overall total, right? But we can do it a lot, actually. So I added a star right here, okay? And then I moved 1 star over here. And we still, again, have 6, 6, 6, 6, 6, 6, 6, 6, 6. I think I added 1 there. That's okay. And right, so I guess that's the last example I did because you can do a little more. The upper limit of this is 4 extra pieces, but I actually have not toyed with if I can do that with maybe a different number of columns or rows or something like that. But there's some neat examples of this existing on YouTube. And if you're particularly interested in seeing actual rocks, there's actual rocks versus little star symbols and semi-acceptable JavaScript. Yeah. So I'm kind of wrapping up with, I didn't put a lot in this part, but Grace Hopper, the address for the building that we were supposed to be in for that talk is Grace Hopper Lane. And I think it was meaningful, so I wanted to mention her. I just had kind of a little bit of a summary. Maybe I'll do a better job when I'm in person, but it's Grace Hopper's application of mathematical thinking to the development of early compilers and programming paradigms fundamentally transformed computing. Her contributions include abstraction through compilers, which allowed programmers to focus on high-level logic rather than machine-specific details. And that kind of feeds into, I think, really a lot of where programming has gone. I'm sure any of you that have had anything to do with programming have heard people either rave or complain or praise that a lot of programming now, people don't really need to know a lot of low level, or they don't need to know this, or they don't need to know that. They can do a lot of high level stuff, come in with all these different plugins, frameworks, UI tools. I'm absolutely attached to my IDE. I love JetBrains, but it's changed, and she was an early reason it went in that direction. She also had formalization of control structures and syntax rooted in mathematical logic and grammar, modular and recursive thinking, which mirrored mathematical problem solving and became the basis for modern programming languages and paradigms. That touches base on some of the things that we talked about here. And then optimization and efficiency, key to both mathematical problem solving and programming, which Hopper applied to early computing systems. In summary, Hopper's mathematical approach helped bridge the gap between human logic and machine execution. Remember, we talked about random numbers and deterministic systems? It's a factor. So that laid the foundation for modern programming languages, compilers, and the structured algorithmic way in which computers solve problems today. Again, the deterministic systems and whatnot is logic. And maybe that's one of the reasons that pi reminds me, pi is next, my bad. That's one of the reasons that math reminds me of that. But now I've given it away because there's pie at the end. You get a slice of pie at the end. This is just it's just part of what I did for Pi Day. I also have there's a repo, but I wrote some code I really wanted to add the ANSI colors to terminal colors because I love the like rainbow colored foreground with black background, and the triangle is the closest that I could get to look like a slice of pie. I thought it was lovely. So I hope you enjoyed the odd speech. I certainly am no professional podcaster or recorder or anything of the sort, but I hope I made you laugh. I hope you thought positive things about number sense and that you probably know more than you think. And maybe you'll go watch some videos of rocks later. Who knows, I'm hoping that someone laughed at my multi-pass comment that I didn't know I made until later. But that's it. Enjoy.